Welcome to the second part of our series on heaps. So at this point you know what a priority queue is, you know what a heap, and in particular a max heap is, and how we are storing a max heap. And what we're going to look at now is how to implement the operations for a max heap, how to efficiently construct a max heap, and how to use this for sorting. So in the first video I showed you this comic, and at this point you know to what extent this is a heap. So you have the max heap property. It is not a nearly complete binary tree. This comic comes with extra text, and this is about the following. If I take out the maximum, how can I rebuild my heap of presence or my heap in general? So that brings us to operations on a heap. What we want to be able to support is insert, maximum, extract max, increase key. Let's start with the maximum. That's the easiest operation. So here we have a heap stored as an array or in an array, and we want to find the maximum. So what's the maximum? The maximum is the element at position 0. So implementing this is very easy. We simply return what is at index 0. Obviously we first need to check that our heap is not empty. What's the running time? The running time is constant. Done. Next operation would be extract max, taking out the largest present. That is not quite as easy. Let's have a look at this in terms of the heap structure. So this is a heap, and we want to take out the 35. So now we have this situation. What can we do? A natural idea here would be to take the largest child, so the 30, and move it up. But then we have a hole here, so then we again take the largest child. We take the largest child, but now we have a problem because we no longer have a nearly complete binary tree because it's not filled from left to right. So this doesn't quite work. So what our algorithm will do instead is that we're first going to make sure that the structure is correct, and then we're going to fix the max heap property. What does that mean? So here we want to take out the 35. Now to get the structure correct, what we were going to do is we're going to remove this node, but then we will have to place a 5 here. So that's what's happening here. So first we check whether there's actually an element to extract. If that is the case, we store it as max because that's what we're going to return. We're not only deleting it, but we also want to return it. Now what we do is we set a 0, so this root element, to whatever was the last element, so the 5. And we're going to reduce the heap size by 1. So the 5 down there will disappear. Now we need to restore the heap property. We have the correct structure, but up here the max heap property is violated because 5 is not larger or equal 30 and it's not larger equal 19. We're going to fix the heap property by a method called Max-Heapify. So Max-Heapify needs to restore the max heap property, and it has a parameter which is here 0, and that specifies the position of the node where I want to fix the max heap property. So 0 means at the root. So what we want to ensure that a heap rooted at position I has a max heap property, and we can assume that the two subtrees, so at left I and right I, so at the left child and the right child, that those are already max heaps. So how does it look like? So here we have a heap or max heap, except that the max heap property is violated at the root. How can we fix that? So we will want to call Max-Heapify for the root. Now to fix the property at the root, we will exchange 10 with its larger child. So we swap those two. Now we have the 10 here. The root is fine, but now the root of what was previously the left child, so here at index 1, there the max heap property is violated. So now we call Max-Heapify recursively, and we call it on that index. So then we swap again with a larger child. So the larger child here is with the key 35. Now the 10 sits here. Again, the max heap property might be violated, so we should call it recursively on this position, and the position here is 4. So 0, 1, 2, 3, 4. Now at this point, I have a key that is larger or equal to the key of the children, or at this case there's only one child. So now the max heap property holds, we can stop, and we have a max heap. How does this look like in code? So if I'm at a node, and it might have 2 children, I will want to find out which of these has the largest key. And I'm calling the index of that node, I'm calling that largest. So I want to find out what is largest, and I do it in the following way. So first I need to check, is there a left child? If there is a left child and it has a larger key, I'm going to set largest to the index of that node, so to left I. Otherwise I keep it at simply I itself. Then I do the same with the right child. Is there a right child? Does it have an even larger key than the current largest? If so, I'm going to set largest to the position of the right child, so right I. If largest is not I, so if one of the 2 children has a larger key than the node itself, then I swap. So I swap AI with a largest and recursively call Heapify or Max-Heapify on the corresponding child, which I can find by simply taking that index largest that I found. What is the running time of Max-Heapify? So what does Max-Heapify do? It takes an element, it possibly swaps it with one of its children, it possibly swaps again and again and again and so on. But how often can it swap? It can swap only until I hit a leaf. So, and that is at most height of that node steps. And the maximum height that I can have, so the height of a max heap, is of order log n, so to be precise, simply at most log n. And an explanation of why the height is log n I gave at the end of part 1 of the series. A different way actually to look at the running time of Max-Heapify is looking at the recurrence. So the recurrence, so the running time of Max-Heapify on a heap of size n is a constant plus the running time on a heap of size n half, because the heaps at the left or right side, both of those have size at most n half. So I get T of n half plus O of 1 here. And using the master theorem or your favorite way of solving recurrences, this again gives me O of log n. So Max-Heapify takes O of log n time. Now extract max essentially just used one Max-Heapify, so that means also the running time of extract max is order log n. So coming back to this comic, opening the root present can be done efficiently, so it's really safe to invite your computer scientist friend to Christmas. Let's move on with insert. So we have maximum, extract max, insert. Now insert I will keep short because there's still increase key to come. We can handle insert by calling increase key. So for instance, if this is my current max heap and I want to insert 10, what do? I first make sure that my heap size is by 1 larger than before. I insert a node with an arbitrary small key. Let's call that minus infinity. This gives me a max heap. So the max heap property still holds. It has the right structure. Now I'm just going to increase this key to 10. And if I succeed in this, I've successfully inserted 10. But of course now if I want to increase the key to 10, I still have to do some work. And that's what we do in increase key. So let's have an example. So here we have a heap. We have this 11 here. And let's say we want to increase the key of the 11 to 42. What do we need to do? We already have the right structure, so that is fine. But the max heap property is violated here. There's a very easy fix. Swap the 42 with the 19. And so on. Now let's have a look at code for this. So first of all, we want to increase key. So if the new key that I have is smaller than my old key, then I'm going to return an error because we're not actually increasing a key. Otherwise, I'm going to set my value to the new key. So far, so good. And now I'm going to move it up until the max heap property holds. What does that mean? So while I'm not yet at the root, and that is I larger than 0, because I equals 0 means I'm at the root. So while I'm not yet at the root and my parent has a smaller key than I have, I'm exchanging myself with my parent, and I'm going to set I to the parent of I. So I'm continuing this at the parent. So this means I'm moving the 42 up to here in this way. So here we move the 19 down, we move the 35 here, 42 is here. I'm fine. That was very easy. The running time corresponds to the length of this path. The length of this path is again bounded by the height of the heap. So the running time is order log n. So now we have order of our operations in the time that we wanted to have, maximum and constant time, all other three in time order log n. So let's wrap up this part about operations with a quiz, namely the following. I'm calling Max-Heapify on this heap here. So I give you the array, it corresponds to a heap, on the root. And the question is, how does the resulting heap look like in terms of the array that stores it? A, B, C, or D. And the idea is that you do Max-Heapify step by step. So and maybe it's a good idea to draw the heap as a heap, and so on. The correct answer here is C. So why is C the correct answer? So let's look at our heap here. We have 1, 6, 5. Let me continue. 4, 3, 2. I'm calling Max-Heapify on 1. I'm going to swap the 1 with a 6. I'm going to swap the 1 with a 4. The result is 6, 4, 5, 1, 3, 2. That is C. Next, I would like to show you an algorithm for constructing a heap. So you might be asking, why do I need an algorithm for this? I already have an insert routine. Why not simply insert the elements one by one? Okay, so if I insert the elements one by one, I get log n, order log n per insertion. I am inserting n elements, so that gives me a running time of order n log n. So the great news here is that we can actually build a heap faster, namely in linear time. So how do we do this? We do this by the following algorithm. And what does it do? So we have as an input some array. So let's say 4, 1, 2, 3. Now we simply interpret this as a max heap. So think of this as being 4, 1, 2, 3. Now obviously the max heap property is violated, but we have a nice way to fix the max heap property, and that is using Max-Heapify. Now to call Max-Heapify, what we need is that for the two children we already have max heaps. So calling Max-Heapify now on 4, that would not work because the children here, we don't necessarily have max heaps. This is not a max heap. But what we can do is we can simply start bottom up and always make sure that we have max heap, and in that way at the end call Max-Heapify here and are done. So that's what this method does. So we start bottom up, so 3, 2, 1, then 4, and always call Max-Heapify. Now Max-Heapify on 3 doesn't make much sense because it's only one node. Max-Heapify on 2 also doesn't make much sense because it's only one node. So we can actually start this at the length divided by 2 minus 1. So at this node here at the 1. So what we would be doing is we call Max-Heapify on 1. This will swap the 3 and the 1. And then we call Max-Heapify on this 4 here. Okay, the 4 is already on the right position. So we're done. So in this way, we have constructed a max heap. So now let's first analyze the correctness of this algorithm and then the running time. Correctness is actually a straightforward loop invariant proof. So here's the loop invariant. It simply states that for all of the nodes that I already processed, I have max heap. So for I plus 1 up to n minus 1, which is the last node, we have that all of these are the roots of max heaps. Now given this, maintenance is very simple because now I'm processing node I. Because for everything beyond I already have max heaps, I can call Max-Heapify on I, because what I need is that the two subtrees at left I and right I, that those are max heaps. So then Max-Heapify on I gives me a max heap at position I. So then I also have it for I here, meaning that pi minus 1 holds. And that's it. So at termination, we have that every node is a root of a max heap, in particular the root node, which then means that we overall have a max heap. That's correctness. Now let's analyze the running time. And the crucial part here is this Max-Heapify. So we know that Max-Heapify runs at O of log n time. Here we do it n times or n half times. So this would give us O of n log n. That's an upper bound, but what we actually want to prove that it's linear. So this is not a tight bound, so we have to look more carefully at this Max-Heapify. And the crucial part here is that we take into account the I. Because Max-Heapify on the node at position I actually has a running time of O of the height of that node. So as a reminder, what is the height of a node? It's the number of edges of the longest path to a leaf. So let's see that by example. All of these nodes down here, they are leaves. So the longest path to a leaf is 0. Then above that I have height 1, height 2, and so on. And the maximum height is log n, and that's why we had this bound of O of log n. But as you see in this example, I mean, most of the nodes are actually at height 0. Then half of the remaining nodes are at height 1. Most nodes have somewhat a very small height, and we're going to make use of that in our analysis. The standard analysis of this running time uses a sum, and I'm going to show that in a moment. But to build some intuition, I want to show you an analysis that uses a recurrence, and that works as follows. So for the root has height log n, so Max-Heapify, we're calling Max-Heapify for this node also, will cost O of log n time, or take O of log n time. We will also call Max-Heapify, we're calling Max-Heapify on all the nodes, so we're also calling it on the children. The children are roots of max heap of size at most n half, so the height is at most log n half. So here I'm going to spend log n half at most, and then log n quarter, and so on, depending on the size of the corresponding sub heap. If I sum up all of these terms, then I get as a running time 2 times the running time of a heap of half the size. So all of the Max-Heapifys here and here, plus this log n. So we're not using a recursion here, but we can still formulate this recurrence for the running time. And now, if you use, for instance, the master theorem, you're going to see that this dominates, and I get a n to the log a base b, n to the log 2 base 2, that is n to the 1. This will give me T of n is of order n. Now let's also analyze this running time by simply summing up all the operations. So what we have here is that a Max-Heapify on node I will take O of 1 plus the height of node I time. And I do this for all nodes. I could skip the height 0 ones, but let's also do those. I goes from 0 to n minus 1. So this is what we want to sum up. We're now going to sum it up first by taking all height 0, then height 1, height 2, and so on. So what do we get in this way? So instead of summing node by node, we do all nodes of one height, all nodes of the next height, and so on. So we have the height now goes from 0 to log n. And we have, so for each of those nodes, I will get 1 plus a height, and height is now called h, 1 plus h. And I get that for every node, so I take this times number of nodes with height h. Now the question is, how many nodes do I have of a certain height? If I have n nodes overall, how many nodes do I have at height 0? This is actually n half. So half of the nodes are at height 0, then half of the remaining ones, n quarter, are at height 1, half of the remaining ones are at node height 2, so n eighth, and so on. So what I get here, so this sum here, is the same as h goes from 0 to log n. So I have this 1 plus h, and the number of nodes at height h is n divided by 2 to the h plus 1. So for height 0, this is n divided by 2. So what I have here is, I have this n, which I can take out of the sum. So what does that give me? So what I get is, so let me have an O of n outside. So now the n is outside. What remains is a sum over all the heights. And now I have 1 plus h divided by 2 to the h plus 1. So let me write this as h plus 1 divided by 2 to the h plus 1. So what does this give us? So if we wouldn't have this h plus 1 here, we would actually have a geometric series. So we would have, so it starts at h plus 1, so that's 1/2 plus 1/4 plus 1/8, and so on. Overall, this is smaller than 1. This is if we wouldn't have this h plus 1, but we have the h plus 1. But what does the h plus 1 give us? So we can see this as having this 1/2 term only once, the 1/4 term twice, so let me write it again here, the 1/8 term 3 times, and then the next term 4 times, and so on. Now if you look at this like that, then okay, we had that this was smaller than 1. Next I have the geometric series, but starting at 1/4. So that will be 1/4 plus 1/8 plus 1/16. That is smaller than 1/2. Then I have the geometric series starting at 1/8. So that will be overall smaller than 1/4. So if I take into account the h plus 1, then I actually can rewrite it to get this sum here, 1 plus 1/2 plus 1/4 plus 1/8, and so on, and that is smaller than 2. So overall we have a sum that is smaller than 2. O of n times that sum is in O of n, and that is the running time of Build Heap. To understand how Build Heap works, it's good to simply try it by hand. So that's what I propose that you do. Do Build Heap simply step by step on the input 1, 2, 3, 4, 5, 6, 7, 8. And then the quiz is, what do you get? A, B, C, or D? The correct answer is C. And why is that the case? Let's simply execute it. So we have 1, 2, 3. We have this as input. And now we call Max-Heapify starting at the lowest nodes. So the first relevant one is here, the 4, we swap 8 up. Then here we swap the 7 up. At the 2, we swap the 2 with the 8, the 4 with the 2. Now, we only have to do Max-Heapify on the 1 here. 8 goes up, 1 goes down, but it's swapped with a 5. So we have 8, 5, 7, 4, 1, 6, 3, 2. That's C. Let's use heaps, and we're going to use heaps for sorting, and the resulting algorithm will be called Heapsort. So the sorting problem was, we have given a sequence of numbers and we want to reorder those numbers, so we want to compute the permutation such that the numbers are in increasing order. And when we look at sorting algorithms, we're always interested in how efficient are they. So what is the running time? Another property we were interested in is the algorithm in place or not? So do we only need a constant amount of extra memory? We've seen a couple of sorting algorithms and they all had their shortcomings. So selection sort has a quadratic running time, so that is not good. It is in place. Insertion sort, quadratic running time in place. Merge sort is efficient. It takes order n log n time, but it is not in place. So we were swapping out the elements into auxiliary arrays and then back again. Heapsort gives us both. It runs in order n log n time, so that is optimal in the comparison-based model, and it is in place. So let's see how it works. So this is Heapsort. What it does first, it builds a heap. Let's look at this by example. So let's assume I have an input. Let's say I have 3251 as input. When I now build a max heap, I will get 5231. So let me draw that, 5231. So that's the result of build max heap. Now the algorithm will build the sorted order from back to front. So I first want to find the last element. The last element is a maximum. Good that I know where the maximum is. It's at the top of my heap. So what am I going to do? Let me swap the 1 and the 5. 1 goes here, 5 goes here. Now I forget about the 5 in the heap. So 5 is on the right spot. The 1, obviously, in terms of heaps, is not at the right spot. So I have to call Max-Heapify. Max-Heapify will move the 1 down here. So I will have this now. 3, 2, 1, 5. So let's look at what I did here. So I swapped the first element with the last element to get the maximum to the end. I reduced the heap size by 1, so I ignored the 5 from now on and called Max-Heapify on the root. And I do this now again and again and again. So I'm going to swap the 3 and the 1, and I'm going to forget about the 3. So now I have 3, 5 at the end, so that's sorted. I have 1, 2 as my heap. I still have to again fix the heap property. I do this with Max-Heapify. So then the 2 is up here, the 1 is there. Now I'm at the next step where I swap 2 and 1. Now I have everything 5, 3, 2. This part is sorted. And actually I can stop. So now I have 1, 2, 3, 5, which is indeed the sorted order of these numbers. That's Heapsort. Let's look at correctness and running time. Correctness. We have a loop. We do a loop invariant proof. What is our loop invariant? So what do we maintain? For the last part of the array, we have that part already sorted. And in the first part, we have a heap of the other elements. So how does that look like as a loop invariant? So in I plus 1 up to n minus 1, we have the correct number, so at the n minus I minus 1 largest numbers sorted. So that part is already sorted. And then in the remaining part, so from 0 up to I, we have a max heap on the remaining elements. And then for the maintenance, we simply need to make sure, first of all, that we maintain the first part, but taking the maximum of the remaining elements and placing that on position I will give me that part of pi minus 1, and then the calling Max-Heapify will make sure that I have a heap on the remaining elements. What is the running time? So it's dominated by this Max-Heapify that takes order log n time. We do this n times, or n minus 1 times. This gives me order n log n as a running time. And again, the best way to get to know an algorithm is to execute it by hand. So that's the goal of this quiz. So we have as input 25314. And now I would like you to execute Heapsort on that input. Of course, if you would execute it up to the end, then the answer is very easy. It will be this sorted. So what I want you to do is do the first 2 iterations of this loop. So build Max-Heap, obviously, as a first step, and then 2 iterations of the loop, and what is the state of the array after that, A, B, or C. The correct answer is A. Let's do this together. So the input is 25314. We first do build heap, which means we call Max-Heapify bottom up. We don't need to do the leaves. 5 Max-Heapify is already fine. We have the heap property here. 2, we need to swap 2 with 5. So then the 2 is here, the 5 is here. Now, recursively call Max-Heapify here, moves the 2 down here, the 4 here. So now our heap is 5, 4, 3, 1, 2. Now we do 2 iterations of Heapsort. First iteration, swap the 5 down here. 5 goes here, 2 goes here. Ignore the 5 from now on in the heap. Call Max-Heapify on the 2. That moves the 2 down here. We have 4 here. We have 2 here. 2 is not swapped with 1. Now, second iteration. 4 is swapped with the last element in the heap. That's the 1. 4 goes here. 1 goes here. Max-Heapify on 1 swaps the 1 with the 3. 1, 3. Our new heap is 3, 2, 1, 4, 5. That's A. So what did we cover? In the first video we saw priority queues, we saw how heaps work, how heaps are stored. Then in this video we saw heap operations, build heap, and heap sort. That's all for now. See you next time.